Okay, problem 2.30b reads, use Gauss's law to find the field inside and outside a hollow cylindrical tube, which carries a uniform surface charge sigma. And then we're going to check the results if it is consistent with equation 2.33. Okay, so I took the liberty of writing here 2.33. So 2.33 generally describes if we take the if for a boundary, typically it's in a form of a surface. Okay, the electric field in this case above and below, the difference of that is just equal to the charge density divided by epsilon, which is reminiscent of Gauss law. Remember what is Gauss again? The integral of E dot dA, this is equal to Q enclosed over epsilon sub 0. Okay, so this is your Gauss's law. Now, let's compute for this. Okay, so let's first draw our long, hollow cylindrical tube. So you will notice here it is long. Okay, so this is already a clue that the side of the cylindrical tube will not affect the computation. It is hollow, so that means there is no charge inside, and it is a cylindrical tube. Okay, so if we're going to draw that, it would look something like this. So this is your cylindrical tube. This is one side. And this is another side. And then this is the sides of your tube. Okay, so this is a long cylindrical tube. So you will notice that from the figure itself, we're going to use cylindrical symmetry. Okay, now first, as I mentioned, is we calculate because we're calculating the field inside and outside a long cylindrical tube. So we're going to have two cylindrical Gaussian surface. One inside, okay. So this is your Gaussian surface inside. Okay, so this can be defined as follows. So this will be the length of the cylindrical surface. Let's call this L. And then from this axis, okay, we can define this as S. Okay, so this is inside. And then we can write the the Gaussian surface outside. So let's say this will be the Gaussian surface for the outside. Okay, it can be here, but for simplicity's sake, we can write it here. And then this one and this one. Okay, so here we can define this length to be L, which is different from this L. And you will notice later that because of the fact that we have a long cylindrical shell tube, this L will not actually matter. Okay, okay, let me just complete this one, and then This will be our S for the outside surface. Okay, so as I mentioned, let's start with inside. Inside. Okay, inside, S is less than, let's call this R in the meantime. This is R. So S less than R. So that's inside. So first, as I mentioned, let's calculate Q enclosed. When we wrote this cylindrical Gaussian surface, we can see that the enclosed charge or the charge enclosed by this Gaussian surface is 0. Because remember that the charges are on the surface. So that means inside this hollow cylindrical tube, there are no charges. Okay, so Q enclosed would be equal to 0 because it's hollow. So therefore, by Gauss law, the electric field is equal to 0. Simple, right? Dali lang, di ba? Okay. Outside. What about outside the cylinder? So that means S is greater than R. So as I mentioned, let's calculate first Q enclosed. So Q enclosed will just be equal to, okay, remember when you say Q enclosed, that's the enclosed charge by this Gaussian surface. So in this case, that enclosed charge will be this. This and this. Okay, so if we're going to visualize this, the enclosed charge will be this part, as well as in the other side. Okay, so this is a cylindrical section of the cylindrical tube. So the surface area of that, the surface area of this is just equal to L times 2 pi R. We know that Q enclosed is just equal to sigma, that's density, times area. So in this case, this is 2 pi L R times sigma. This closed integral E dot dA, as we saw earlier, can now be equal to integral of E dot dA1, where dA1 is the area vector on the side. So this is already an open integral because the next electric field, the next area integral 2 and 3 are essentially 0 because dA2, which is in this direction, and in this direction is dA3, the direction of the electric field, which is along S direction, radially outward, is perpendicular to dA3 and dA2, so the dot product is 0. Okay, we know that the electric field here is uniform because of a uniform charge density. So here we expect this to be equal to E times the integral of dA. 1, which is the total area of the side of the cylindrical Gaussian surface, which is equal to what? Q enclosed over epsilon sub 0. So simplifying this, we now have E times the area of this Gaussian surface, which is 2 pi s times L. And then Q enclosed would be equal to 2 pi L R sigma. Then we divide it with epsilon. And in this case, the electric field will now be equal to, here, 2 pi will cancel. L will also cancel. So we now reduce to sigma R divided by epsilon naught S. SF. This is now the electric field outside. Now let's see if this is consistent to this result. Okay, so if this, in this case, the electric field above will be electric field outside, and then the electric field below, we can choose inside. Okay, so that means we're going to use this electric field above or outside will be sigma R over epsilon S. But we know, but this one is on the surface. So that means R is your S. So in this case, this becomes, this is minus 0. Okay, if R is equal to S, therefore, these two will cancel. So this is equal to, indeed, sigma over epsilon, which is the same as this one. And then, of course, n hat would still be equal to s hat, so because there is an s hat here. Okay, so this is consistent to our result.